Okay, the talk will be about higher order MSL Horn constraints, a paper by Jerome Jochems, and he will get the presentation. Eddie Jones and Stephen Ramsay. Please.
Hi everyone, I'm Jerome Jochems, and I'll be talking to you about high order MSL Horn constraints, which is my joint work with Eddie Jones and Stephen Ramsay. So right, first I'll give you a sort of intro to MSL as we know it, the what and the why of it, and how we can decide satisfiability for this fragment, before diving into our contributions, which is lifting this fragment and its benefits to higher order. And finally, I'll wrap up with a bigger picture as to how this fits into the wider higher order verification landscape. Right, so MSL Horn constraints, first of all, they are just Horn clauses of first order logic, like these, for example, over natural numbers with an odd and even predicate. You have a function symbol 0 and a successor s. These are also Horn clauses of first order logic, just with more variables. These state whether an expression that's a multiplication is odd or even. And is also a Horn clause, because technically a Horn clause is a conjunction of literals with at most one positive literal. And the positive one is the head. And if there's no positive literals, then the head is false, empty. Yeah, and the part on the left-hand side of the implication we call the body. Right, the MSL restriction applies to heads only. And these must be monadic. So they could be a predicate of one argument, but not of two or more arguments. It must be shallow. So they can have at most one function symbol in the head applied to some variables, but nothing more complicated than that. And they must be linear, which means that all the variables in the head must be distinct. And again, all these clauses here that I've provided are MSL clauses themselves. That's not quite true. Yeah, sorry, yeah, they are all MSL clauses. So why are we interested in this fragment to begin with? First and foremost, because it has decidable satisfiability, unlike first-order Horn clauses in general. And what's the point of having a decidable problem if you can't actually use it in practice? So yeah, it does have applications in static analysis and verification. And there's also something natural about this fragment. It doesn't feel contrived or artificial. And this is sort of witnessed by the fact that it was discovered by at least 2 different groups of people independently. So right, how do we decide satisfiability for MSL? Well, we start with a set of clauses and construct an every satisfiable set of automaton clauses using a specific kind of resolution. So of course you might question, well, what are automaton clauses? What's the crystal resolution? And why on earth would that be decidable? So I'll go through all these questions as I go. Automaton clauses are just MSL clauses with a specific shape. And the body can only contain very shallow atoms. So a predicate applied to one bare variable. And this variable is required to be a part of the head. So let's check our running example. If we look at the first criterion, there's only one clause that violates this, namely this one, because the atom in the body contains two function symbols, 3 function symbols actually, and it's not allowed any. And for the second criterion, only the last clause violates that, because the X is not bound by the head. Right, so in general, we have finitely many predicate symbols, finitely many function symbols, which means that there are only finitely many automaton clauses. Of course, up to the renaming of bound variables and by treating the body of the clause as a set, such that duplicate atoms are only really counted once. And this is a key part to decidability, the fact that there are only finitely many automaton clauses. Right, so we transform MSL clauses to automaton clauses, and the whole point of this is that checking satisfiability for these automaton clauses is straightforward. And in fact, as straightforward as setting no emptiers for finite automata. You might have already spotted the similarity there. So if automaton clauses like this, that correspond to automaton transitions pretty directly, just a syntactic correspondence. But of course, in MSL, not all our clauses have a single variable. You may have no variables or 2 variables. So technically, we correspond to 3 automata rather than just word automata. Right. So how do we now go about constructing the set of automaton clauses now that we have identified those? Well, we use resolution, just standard resolution really, but we use an automaton clause as side condition. So for instance, this one that we saw before, if you multiply 2 odd numbers, the result is also odd, and we resolve into the body of a non-automaton clause, like this one. So in particular, that means that we want to unify these 2 atoms in red. So in particular, it means we want to unify these terms, Z1 with S of X and Z2 also with S of X. So if we perform resolution, what we do is we make this unification and then take the body of the side condition, insert it into the main clause under the substitution, like that. And as I mentioned before, we treat the bodies of automaton clauses as sets. So this is really just equivalent to saying, well, we only have one atom there. Now, if you look closely, you see that we have sort of stripped away a function symbol. We've gotten rid of mul. And that's precisely what resolution with an automaton clause does. It just stripped off a constructor. Which means that the conclusion is strictly closer to being an automaton clause than a premise. Because remember, we're not allowed any constructors in the body of an automaton clause. So if we keep repeating this, keep applying resolution with automaton clauses, eventually we'll end up with just automaton clauses. And it will terminate and saturate. So starting with a set of MSL clauses, we just keep applying resolution until we end up with a set of automaton clauses. And yeah, the key part is here that there are only finitely many automaton clauses. And that, yeah, this is a well-founded order that's going down strictly. Yeah, and this is sound and remarkably complete for the MSL fragment. So this brings me to our contributions, which is lifting all this to higher order. Can we do that? Yeah, of course we can. Otherwise, we would not have been here. So yeah, our first contribution is just identifying these fragments and how they relate to one another. For the sake of this presentation, I'll consider a higher order just as higher order function symbols. Like for instance, here we have an F that's applied to X, but X is itself first order, so F is second order. And this means we'll have to adjust the notation a little bit, because in the higher order setting, we may have partial applications, like F of X without the second argument being provided. But can we also preserve all the benefits of MSL? Yeah, of course we can. So we still have decidable satisfiability. There's still a notion of naturalness, because it turns out that higher order MSL corresponds to the higher order Jochems safety problem and intersection refinement typeability, which are 2 well-known approaches to higher order verification. And we also have applications. And we have provided a sort of proof of concept implementation of verified soccer programming in Haskell. And in this talk, I'd just like to focus on deciding satisfiability, because this was highly non-trivial. Right, so in the first order setting, we take these MSL clauses, apply resolution, obtain actually satisfiable automaton clauses. But in the higher order setting, we encounter a unique challenge, which is resolving into variable-headed terms. So for instance, we could perform resolution here using this automaton clause in a box into the main clause, where the predicate P applied to f of x, sorry, p applied to x1 of something, x1 itself being a variable. Well, yeah, we have to unify x1 with g of y1 and y2 with x2, x3, resulting in this unifier. So if you do this naively, we will have to end up instantiating the x1 in the head of this clause, like this. So now we have made a deep head that's not automaton, this clause. It's also not even MSL anymore. And yeah, this is definitely a problem because we want to keep applying this resolution process, which means we might end up increasing the depth of this head and getting further and further away from MSL. So yeah, this does actually kill decidability. Now you may argue, do we have to instantiate the head? Do we not just put it as a constraint in the body? And yes, we can. Still problematic for us though, because this is a higher order equality, which is generally a hard problem. And again, if we keep applying resolution, this constraint, this equality will keep getting more complicated as well. So thankfully for us, this is already much stronger than what we actually need. What we actually need is just that x1 behaves like gy1. And specifically, it behaves like gy1 in this particular automaton clause. So this is what we do instead. We nest an automaton clause, which is just the automaton clause we started with the substitution undone, if you will, and insert it in the code. Now, of course, this looks even much more dangerous than the head substitution, but I'll try and convince you that it's not as dangerous as it looks. Yeah, giving you a conclusion, definitely outside of MSL, but in a harmless way. And why? Because this next clause is itself automaton. It's just the first order automaton clause that constrains its single free variable x1, much like the outer clause constrains f. So our solution to this high order challenge is to allow higher order automaton clauses that are nested in a stratified way and that are monadic. So what do I mean by this? PA is an automaton clause because P constrains the null symbol A, and we can then take this automaton clause and put it in the body of a first order automaton clause, like that. But now this P does not constrain the top level A, it constrains a local variable Z1. And again, we can continue this process, taking the first order automaton clause, putting it in the body of the second order automaton clause, where instead of B, we now constrain local variable Y1. It's for third order, etc. automaton clauses. But it's important to note that each automaton clause, no matter how nested, only really has one subject, it's monadic. So these four outer clauses, they constrain A, B, C, and D, respectively. That is not too dissimilar from the first order automaton clauses and the body of theirs, like PA, always contains a single variable locally constrained. Right, so we claim that using these high order automaton clauses, we can decide satisfiability for high order MSL. So let's see a little bit of it in action with a concrete example. This was our running example, part of it. And let's extend it with some higher order clauses, like the map function, which takes two arguments, a function and a list of integers, and it just applies the function pointwise to the list. And we introduce a new predicate EL, which is even list, that denotes that all the elements in this list are even. So of course, if the list Z is empty, then trivially this is an even list. Or if Z is composite, then F applied to the head must be even, and the remainder of the list must also be even. So let's try to resolve into the red atom over there, which means we have 3 candidate clauses, because this is a resolution step into a variable header term, f. And let's just choose the last automaton clause, number 6. Right. So we're going to perform a resolution step, which means we have this substitution. F needs to unify with more x and y with head of z. And of course, if we do this naively, like we've seen before, we will end up increasing the depth of the head like this. But we've learned better now, so we just skip that and go straight to automaton resolution in the higher order setting. So what we've done, we've taken this automaton clause 6 to now constrain f, because we're not quite really applying the substitution f to more x. We're just saying f behaves like more x, specifically in clause 6, the part in red. And the blue part of the substitution is still being accounted for by the body of the automaton clause with the substitution applied. And this is now closer to automaton form, would you believe it? Because we started off with an atom that concerned 2 variables, f and z, and we have now separated these 2 variables. The red part only concerns f, and the blue part only concerns z. And yeah, the intuition behind this clause is of course, if f preserves evenness, which is the red part, and z is a list of even numbers, which is the blue part, then that z denotes a list of even numbers. So let's recap the contributions. I've mostly focused on decidable satisfiability here, but I'd like to make a quick note about number 3, and in particular about intersection types. Because intersection types correspond to higher order automaton clauses. So for instance, take this mol type here. It corresponds directly to these 3 automaton clauses we've seen before. And the T, the top in the type, corresponds to the empty intersection, which means no restrictions, no constraints on this variable at all. Like you could see in the second and the third clause. And of course, yeah, we can nest this again in higher types. So how does high order MSL fit into the high order verification landscape? Well, thanks to this correspondence with intersection types, we were able to show satisfiability is equivalent to intersection refinement type ability and the high order Morse and safety problem. Right, but what is high order Morse and safety? It concerns a high order recursion scheme, which is a specific kind of high order grammar, and a tree automaton with a trigger acceptance condition. And it then asks the question, well, does this automaton accept the potentially infinite value tree generated by this recursion scheme? And high order model checking has been one of the most well-studied approaches to high order verification over the last decades. But it's also esoteric, as this problem statement shows. It concerns a very specific kind of high order grammar and a very specific kind of tree automaton that's hard to really grasp if you're not already an expert in the field. But thanks to our theorem, high order model checking safety can now be understood as a set of decision procedures for higher order MSL, which is just a fragment of higher order logic. So we have recast safety problem of higher order model checking as a satisfiability problem for higher order logic. And we have used a variant from standard resolution to achieve this. So yeah, by characterizing this very esoteric problem in a purely logical way, we sort of contribute to establishing high order logic as a foundation for high order program verification, because the high order program verification landscape is quite fragmented. It concerns a lot of very specific problems, and high order logic could be a common framework in which to understand and compare these. Much like first order logic provides a common framework vocabulary for first order verification, it being more accessible. Okay, thank you very much for your attention.
Thank you very much. Any questions?
So about the last remark, how do you compare with the attempt at using high order fixed point logic? That's also, in a sense, a way to express high order model checking problem in logic.
Yeah, that's a good point. I think in general, the sort of horn clause representation is still a bit more accessible than high order fixed point logic because you are staying purely within high order logic. You don't have to introduce any constructs at all. But at Drury, that's another approach to achieving the same aim.
Any other questions?
Okay. Thanks for the nice talk. You mentioned before that MSL has this nice connection to free automata, due to automata clauses. Do you have a similar intuition for your higher order automata clauses, or a more powerful model there?
Yeah, so high order automata clauses correspond to intersection types. And it is well known that intersection types sort of correspond to regular languages in a way. It can defunctionalize the high order bits. So in that sense, it does still correspond to even regular automata if you want, if you accept the exponential blow up there.
Okay, question over here.
You mentioned that the way to decide the MSL. Hi. So the way that you use to decide MSL, both in the high order logic and in the first order case, is to convert it to a set of equally satisfiable automaton. So I'm wondering whether it is easy to convert the models of those two parts. Like if you have a model for the set of automaton clauses, you convert it back to the model of the original code.
I think the model should actually coincide.
So they have the same model?
Yeah, I think so.
Then maybe they should be equivalent, not so satisfied.
Yeah, that's fair.
Good. Okay, I would like to thank the speaker again.